Okay, today we're going to learn about optimization. So if you have not already printed the notes from today, I would recommend doing that because we're going to be using these 7 steps the whole time and it will be helpful to keep them in front of you. And also I would recommend stopping the video and reading through these 7 steps because I'm not going to read these to you. So today we're going to learn about optimization. Optimization is finding minimum and maximum values in real life. So we're going to look at different situations and how to optimize the problems in either to find the maximum value or the minimum value that answers the question. So the first example you might be able to figure out in your head, but we're going to use calculus, and you want to find two numbers whose sum is 40 and whose product is as large as possible. So step 1, if you read the steps before, is understand the problem, read the problem carefully, and identify the information you need to solve the problem and what you have been given. So we've been given that the sum is 40 and that the product needs to be as large as possible. So we know that sum is equal to 40. So step 2 says develop a mathematical model of the problem. And if possible, draw pictures. We can't really draw pictures in this. And let a variable represent the quantity to be maximized or minimized. So we want to maximize the product. So I'm going to let x equal one number. So we always have to define our variables. And y equal the other number. And we're going to figure out an equation to maximize or minimize. So we're going to say the product is equal to x times y. And this is the function that I need to find the maximum of in order to answer this question. So then step 3 says make a second equation with the constraints given in the problem and then get the equation in terms of one variable. So we know the sum has to be equal to 40. So I'm going to say the sum, so the sum of these two numbers would be x plus y, and that has to equal 40. So that's my constraint formula. And the reason that we get that is because when we do max-min problems, we always want it in terms of one variable. We don't have to worry about implicit differentiation. So I'm going to solve for this case in terms of y. So I'm going to do 40 minus x, and I'm going to plug that into my product formula in order to get it in terms of one variable. So the 4 steps says determine the domain of the function, determine what values of the variable make sense in the problem. So we most likely won't be dealing with negative numbers since we want the sum to be 40. So we're going to say x is greater than 0 and y is greater than 0. So those are my constraints. And then steps 5 says find the critical points and endpoints and find where the derivative is 0 and fails to exist, because that's what critical points mean. So the easy thing to do is always multiply these problems out if possible, because then I don't have to use product rule. So I'm going to take the derivative, which is 40 minus 2x. I'm going to set it equal to 0 and then solve for x. So if I solve that, I get x is 20, and that's the only critical point we have. Okay. So then we're going to use the second derivative test to determine if it's a max or min. And if possible, if there are endpoints, which there aren't really in this case, you need to plug those in as well to check if those are your possible answers. So I'm going to take the second derivative, which the derivative of 40 is 0, of negative 2x is negative 2. This means that at x equals 2, p is concave down, and x equals 20 is a max, which is what we need because we need to maximize the equation. And then it says, interpret the solution, answer the question by writing what was asked for. So we found that one of the numbers is 20. They said find the two numbers. So to find the second number, I just plug 20 in for x for my y equation. So I'm going to do y equals 40 minus 20. So y equals 20. So the two numbers are 20 and 20. And make sure they make sense. So 20 plus 20 is 40, and then 20 times 20 gives me 400, which is going to be our largest product. And that's how we do the steps for optimization. So that was an easy problem with it. We're going to do a little bit harder problems for this. So here are our steps again. And in this time, we're trying to design a 1 liter oil can shaped like a right circular cylinder. And what are dimensions for the least material? So we have a cylinder. Okay. And we want the least amount of material. And they told me the equation for volume and surface area. So always look at units. It's a key thing. So this 1,000 centimeters cubed, we just know that because it says centimeters cubed, that has to be my volume. Okay. And that we're trying to maximize surface area because it says what dimensions will use the least material. When we're talking about the material around the can, that's going to be surface area because it's how much area surrounds the outside. So step 1, I have the steps written on here. So step 1 says we're trying to minimize the surface area. So understand the problem. We're minimizing the surface area. We're given the volume of the can. We need to develop a mathematical model for step 2. So that means the surface area, they gave me the formula, is 2 pi r squared plus 2 pi rh. For step 3, we need the second equation. So they told me volume is 1,000, so I'm going to plug 1,000 in for V in my volume equation. Now the goal is we need our surface area formula, our step 2 here, in terms of one variable. So I'm going to solve this equation for one variable. If we look at it, h is easier because I don't have to take the square root. So I divided by pi r squared, and I got h is equal to 1,000 divided by pi r squared. And then if we plug that back in, for h, we get this equation here, 2 pi r squared plus 2 pi rh times 1,000 pi r squared. And if you simplify it, the pi and one of the r's cancel. And then we get, this should actually be 2,000 over r. Okay. So this is my simplified equation. And then we want constraints. Step 4 is determine the domain of the function. So r cannot be negative, so r is greater than 0. And then we take the derivative in step 5 to find the critical points. So if we look at this, the derivative of this function is, I bring down the 2 because pi is a constant, so it's 4 pi r. And then I'm going to make it r to the negative first. So this is the same as if I change this to r to the negative first. And if I take the derivative, I get negative 2,000 r to the negative second. And that simplifies to 4 pi r minus 2,000 over r squared. So to find the critical points, I'm going to set it equal to 0, and I'm going to solve it. So if we do that over here, I have 4 pi r equals 2,000 over r squared. If I get r out of the denominator, I have 4 pi r cubed is equal to 2,000. And then if I have 2,000 divided by 4, I get 5, so I get r cubed is equal to 500 over pi r cubed, or pi. Okay, so I did 2,000 divided by 4 pi, and then 2,000 divided by 4 gives me 500. It's still over pi, and then I have to take the cube root. So that's my answer for the radius. The step 6 is I have to take the second derivative. So here's the second derivative. 4 pi r is 4 pi. 2,000 r to the negative second is 4,000 r to the negative third. I'm going to plug in, this is just the second derivative test, so I plug in my radius to that, and if you use that value, you'll get the exact value. It's positive, so the critical point is a minimum. The only endpoint is r equals 0. And we can't have a 0 surface area, so that's not possible. And then the last part is to answer the question. So it said dimensions. So not only do we need the radius, but we need the height. So I simplified this, and you get 5.42. And then if you plug 5.42 into this equation up here, we can get the height, which is 10.84 centimeters. And make sure your answers, guys, are always 3 decimal places, even though these are only 2, because the AP exam wants at least 3 decimal places. Okay, so let's try one problem together. So for this one, we have a square base and an open top, and it has a volume of 4 cubic feet. And we want to find the dimensions that require the least amount of material. So we want to minimize, and we're using material again, so we're minimizing surface area, and we're given volume is 4 cubic feet. Again, units are cubic feet, so that gives it away. Okay, so it might help to draw a picture of it. You can probably draw a better cube than I can, but this is my box that's on its side. Okay, sorry, that's really bad, but it's a square base. So I'm going to say this is x and x, and my y is there. So I'm going to define my variables. So x is my length of my base, and y is the height of the box. And so we need formulas. We need to develop a mathematical model for the surface area. Okay, so we have an open top, so I'm not counting this side. To find surface area, I find the area of each side and I add them. So the area of the base is x times x, which is x squared. And then I'm going to add the area of the sides. One side is the length of the base times the height. So that's x times y. And if you think about a cube, it's going to have 4, or a box, it's going to have 4 equal sides. So I'm going to have 4 times xy. And that's my area, my formula for surface area. For volume, if you remember from geometry, volume is the area of the base times the height. So the base, area of the base is x squared times the height. And that's my volume formula. And I'm going to let 4 equal x squared times y, so that I get my second equation to help us get this in terms of one variable. So the easiest one is to solve for y. So I'm going to solve for y, and then I'm going to plug it back into my surface area equation and simplify. So if I simplify, I get x squared plus 16 over x. And that is my surface area equation. Okay, we are trying to minimize because it's the least surface area. So I need the derivative, and I'm just going to change this to a. So I have a. The derivative of a is 2x minus 16x to the negative second. And I'm going to set that equal to 0. So if I set that equal to 0, I get 2x is equal to 16 over x squared. I can multiply this other side by x squared, so I get 2x cubed equals 16. X cubed is equal to 8, and then x is going to equal to 2. Okay, so that is my critical point. Now, I skipped step 4, determine the domain. So if we come back to here and we look at this, if we're looking about bit length and height, we can't have negative values and we can't have 0 because then there would be no box. So x has to be greater than 0 and y has to be greater than 0. So these are my endpoints, but again, they don't make sense, so I don't have to plug them back in. Now we have to make sure this is a minimum. So in order to do that, I do the second derivative test. I take the second derivative, which is going to be 2 plus 32 x to the negative third. I plug in my 2 to see if it's a positive or a negative. And all we care about if it's positive or negative. So if I have positive plus a positive, so this is going to be a positive number, which means at x equals 2, the surface area is concave up, and x equals 2 is a min. So we made sure that it's a minimum, and then the last step is to answer the question. So we need the dimension, so I need to find the y value. So I'm going to plug in 2 for x in the y equation, and I get 1. And so I'm going to say that the dimensions to minimize surface area are a base length of 2 feet and a height of 1 foot. Okay, and so that's your answer. You have to make sure you answer the question and always include units. Every time you have to include units. Okay, so we're going to do one more example, and there's a few more examples on here if you want to try, and then there's some in your textbook that you're supposed to try for homework as well. Okay, so for this, we have a builder who wants to build a rectangular pen. So I'm going to draw a rectangular pen, and they want to partition it 3 times. So I'm going to have 3 parallel partitions, and we have 500 feet of fencing. So again, feet, it's not squared, it's not cubed. When I talk about fencing, I'm talking about the outside, how much there is. So that's going to be perimeter. It's 500 feet. What dimensions will maximize? So we want to maximize area of the entire pen. So we don't care how many partitions, we just want to maximize area. So if I think about area, let's let x equal the length, y be the width. Okay. Now, we can just call this whole width y. We don't need to say each part because it doesn't matter, because when we find the area, if we call our outside parts x, the area of the whole pen is just x times y. Okay? We don't have to find the area of each part and add them together because it's the same thing as the whole thing. But when I talk about perimeter, we're counting all these side partitions, and since they're all parallel and the same length, we have these things. So we have to count. We have 5 lengths of x. So I have 5x plus 2y, and that's going to equal 500, which is my perimeter. So that's my constraint equation. So here's my mathematical model that we're going to maximize. This is my constraint equation. I'm going to solve for one of the variables. It doesn't really matter which one. I'm going to just solve for y. So if I solve for y, I get y is equal to 250 minus 2.5x. And I'm going to plug it into my area formula to get one variable. And always simplify as much as possible so the derivative is easy. So I have 250x minus 2.5x squared. Okay, so now I'm going to minimize this by finding the critical point. So I take the derivative, which is 250 minus 5x. I set the derivative equals 0 to find my critical points. So I get 250 is equal to 5x, and then x is equal to 50. Okay, we have to check if it's a max or a min to make sure we're maximizing it. So to do that again, we take the second derivative. So if I go back to my equation, my second derivative is just negative 5. So everywhere is concave down. So at x equals 50, a is concave down. And x equals 50 is a max. Remember, if you're not sure, draw your graph, and then the critical point's always the highest or lowest. So this has to be a max because it's concave down. Okay, after we do that, we did our second derivative test. We need to answer the question. So what dimensions? So we have the width, or we have the length of the pen. We need the width. So we need to plug 50 into my equation for y to find the width. So I have 250 minus 2.5 times 50. If I do that, 2.5 times 50 gives me 125, and if I do 250 minus 125, I get 125. Okay, and my units are feet. Now, we also have to make sure that there aren't any endpoints. So again, if we come back, our restraints, x has to be greater than 0 and y has to be greater than 0 because it does not make sense to have a negative side length. Okay. Okay. And again, we can't have a side of 0, so we don't have to worry about our endpoints. And then we just want to answer the question. So the dimensions that maximize area are 50 feet by 125 feet. Okay, so on this, there are 3 more problems. I would try number 3. We're going to do 4 and the last one, 5, in class tomorrow. And there are 3 problems to try from homework on optimization. So in your book, in section 5.4, try numbers 1, 3, and 25, and then read through section 5.4 to see the different examples. Also try number 3 on here and make sure you can do this. This is very similar to number 1 that we just did, except now you're doing the opposite. They gave you surface area and you need to maximize volume. So it's a little bit harder to solve. But try that problem and the 3 in the book, and then tomorrow in class we'll go over this and practice more problems.